Welcome to the 8th episode in a series where I'm doing a total rebuild of my cheap CNC3018. In this episode, I will show you how I made a DIY brushless spindle for my rebuilt CNC3018. Now, it ended up being a pretty huge episode with multiple sections, so skip around as it suits you, or you can watch the whole thing. I'll leave it up to you. Now, it's probably important to point out up front that there are heaps of off-the-shelf spindles that you can simply go out and buy. And as with the CNC rebuild, for most people, it likely makes more sense to simply just go and buy an off-the-shelf solution. But even so, my personal goal is to hopefully make something that works as good as something I could just buy. And of course, the cash spend should be no more than what it would cost me to buy an off-the-shelf solution. Otherwise, it'd be just silly, right? And no, the time I spend making something does not come into the equation, because this is a hobby which I enjoy doing, and nearly all hobbies cost money. So in fact, you could say the time I spent making this thing is actually a cost savings, not a actual cost. Anyway, looking at my AliExpress purchase history, it seems that I bought a bunch of stuff to make this spindle way back in June 2022. So I've actually been intending to do this project for some time now. The basic idea was to use a brushless motor like this one I use with my mini lathe and somehow turn that into a spindle. These motors seem to be originally intended to be used with small mobility vehicles, but even so far it's been working really well with my mini lathe. But I actually chose a different motor to this one that I use my mini lathe. This one is actually a 63/64 200 kV motor. The diameter is 63 millimeters, so that's actually a little bit too big for my mount, and the kV is probably a little bit too low. So what I chose was a 50/56 330 kV motor for around about $35 US. The 50 millimeter outer diameter looked like it was going to be a good fit for my 52 millimeter mount on my CNC, and the 330 kV should hopefully be able to deliver some decent revs too. I also selected a motor that had Hall sensors built in, and my idea here was that I could actually match this up with a DIY ESC, which I'd planned to make at some point. I also bought a 36 volt 600 watt power supply, which cost around about $30 US. This combined with the 330 kV motor should theoretically deliver nearly 12k RPM. And recently when I was looking around for off-the-shelf spindles to sort of make a comparison with, I did notice that many of them are actually paired with this exact power supply. So that actually gives me some confidence that I actually chosen something that's going to do the job. So to adapt this motor so it's going to be able to work with my CNC, my plan was to make a sub body that had its own shaft and its own bearings, and the idea was that this would take away all of the stress from the motor and also provide a method to be able to mount the motor to my existing mount on the CNC. And looking in my files, I actually discovered this original scribble I made a couple of years ago. You can see the idea is to use two large bearings that would take the lateral loads, and then I've also added a thrust bearing at the top there to cope with the penetrating loads as it drills. You can also see these parts here with the hashing. They would probably be 3D printed elements, and they would actually locate the various bearings. So based on this design, I also ordered the main bearings, the thrust bearing, and a new ER11 chuck, which is compatible with my planned 10mm shaft. In total, I think the cost was around about $10 US for all of that stuff. So ignoring all of the bits and pieces which I would use that I already had on hand, I think my outgoing cash spend for this project was around about $80 US. It's not exactly cheap, it's not that bad either. Now, even though I had originally planned to make my own ESC for this project, I decided it would be biting off too much if I tried to build a DIY spindle and a DIY ESC at the same time. So I guess that's going to have to wait for another day. For now, I'm just going to use the same ESC that I use with my mini lathe. I originally bought 3 of those because they kept blowing up all the time. But thankfully I figured out how those ESCs work and how to fix them. And after I modified the one in the mini lathe so that I use a single MOSFET board layer, it's been pretty good ever since. I've never had another failure. In the end, what I originally thought was a terrible ESC turned out to be actually very useful, and it's actually saved me a heap of money in the process too. I actually have a couple of videos discussing and teaching about how these ESCs work. I highly recommend you check them out if you haven't seen them already. I think they're pretty interesting, so they're worth a watch. I did, however, notice one concern with the idea of using this ESC for this project, however. The original seller's page for this ESC stated they are rated at only 7S, so I think that's around about 29.4 volts max, but the power supply I had already purchased is actually 36 volts. So yeah, is that going to work or not? Don't know. Thankfully, these power supplies are somewhat adjustable with a little potentiometer, so I tweaked it to the minimum possible, which was around about 33 volts, crossed my fingers and plugged it into the ESC, and yep, lots of smoke. So thankfully it was easy enough to repair the ESC. I just replaced the fried MOSFETs, replaced the fried high-low driver IC, and after investigating the voltage adjustment circuit in the power supply, I actually discovered that the potentiometer was simply configured to operate in series. It's not a voltage divider. And when adjusted to the lowest possible voltage, the resistance was actually at the maximum range. So I simply replaced the original potentiometer with a multi-turn one with a higher range, and that allowed me to adjust the voltage down to 29.4 volts, which worked fine. So I was back in business. The downside is I'll have to live with a lower 9.7k maximum RPM until I build my own EC, that is, but I think it's plenty good enough for now. Actually, the only modification I did to this EC was just adding a little fan on top of the heatsink here. I thought that was prudent. And it was easy enough to do since this EC already includes a 6-volt step-down converter, which is actually not used for anything else, and seems more than enough to spin this 12-volt fan at a decent rate. So first up, I did some basic tests with the EC and motor, and everything seemed to be working fine. Testing with a lab power supply, the unloaded maximum speed at 28.6 volts got around about 163 revs per second, or 9,768 RPM, which gives around about 340 kV if you calculate it back the other way. So it looks like it's pretty much in spec as far as I can tell. I also used my little cheap Chinese signal generator to test the ESC using a higher peter-burn frequency of 200 Hz. And I also figured out what the duty cycle settings should be for the stop, slow and fast states. Now, I haven't got this motor locked down very well in this test jig. Even so, it does seem to be making noises that indicate that it may be not so well balanced, and it is generating some unwanted vibration. At higher RPMs, it does seem to calm down a bit, however, so I don't suspect this is going to be a showstopper, and really there's not much I can do about it anyway. So with these basic tests done, I was then confident enough with moving on to actually going ahead and making that sub body for the motor. So for this first part, we're going to be making the drive shaft part of the sub body. And here's the diagram that I drew for that. Originally I had intended to make the shaft so that it actually included the spacer component that sat between the two main bearings, but just before I started machining it, it actually dawned on me that as the top main bearing actually covers the grub screws that will lock the shaft to the motor shaft, that would pretty much make it impossible to assemble. So instead I ended up making the drive shaft as two separate pieces, the central drive shaft itself and the spacer that would slip on later, that's space between those two bearings. So first up, we're going to be making that central drive shaft component. So I'm going to make the shaft out of this 20mm steel rod that I have on hand. And I probably should have cut it off in the chop-off saw, but decided to part it instead. As you can see, it's a bit of a painful process with this mini lathe because there's not much space to work with, so you've got to switch around the bits. So I've got about half the material sticking out there, so I'm actually going to machine half the shaft on one side and then flip it over and machine the other half. And that's going to be pretty tricky because I'm going to have to try and realign it, but that's the way it goes. If I could do it between centers I would, but unfortunately my little mini lathe doesn't have the length for that. So here we've just cut out the hole for the shaft of the motor, and the fit is really good there, as you can see. We'll give it a bit of a spin up test. A little bit of movement, but I think it's going to be fine. So I'm going to cut the shoulder for the thrust bearing first. I mean, I could cut the whole material down to diameter straight off, but that's going to sort of make it less rigid as you reduce material, so better do the stuff that's the farthest away first before you start chopping down the material. I think the internal diameter of the thrust bearing is 13mm, so we'll be trying to reduce it down to that. So skim it off. Close, just a bit on the inside shoulder there, we'll just knock it down with the emery cloth. Yeah, really nice fit. Just do some minor tweaking to the depth here. So the main bearing's internal diameter I think is 17 millimeters, so we're just going to machine this down to the final diameter here. Yeah, I think that's a good enough fit. And with the thrust bearing, sort of goes like something like this. Just clean up all the sharp edges. Do an internal chamfer as well. Now as I'm flipping it over, I don't have any easy way to sort of measure the position relative to the other side once I flip it over, so I'm going to put a reference mark in the material itself, and that's something I can measure off when I'm working on the other side. So I finally got a bit of copper shimmer stock, so I can be a little bit less worried about marring up the finished surface there, which is nice. Still take some care to line it up, best I can anyway. So I'm going to use that reference mark, hopefully to face it to the right length now. See how we go. So I'm just using that mark, and yep, 62.5, we're on the bot. So sort of going against what I said earlier about machining the features at the far end before I machine down the overall diameter, but in this case this is what I've chosen to do. And this should be getting close to the final cut. See how the integration goes there at the joint. Yeah, just a little bit more to go. And there you can see we're just skimming, starting to skim that internal surface of the other side. And now we're really skimming it, yeah. That's looking good. Yeah, it's a little bit looser than the other side, but it still sort of locks up. I think that's going to be fine. Let's try to make a reference mark for the length of the shafts, get some idea on where I'm cutting to. And it's gone. Well. So I have to machine this down to 10 mil, which is the size of the internal diameter of the ER11 chuck that I purchased. Yeah, getting pretty close now. So I'm going to machine this shoulder, sort of integrate it with a round shape so we can sort of get rid of any stress points, or reduce the amount of stress points anyway. And hopefully lock this down to the final dimension here now. Looking pretty good. Just a little tight. Don't know why, it should be the right size. Yeah, it's really weird. Actually, there's a bit of a lip on the inside edge here. So I file that down a bit and it goes on fine. Actually, that internal fit is really a bit weird with that chuck. So chamfer off the end, finishing touches. And this edge is pretty sharp too, so I'm just going to knock it down too. And there you have it. It's looking pretty good. Just like I bought one. So we're using the same material as the shaft. Obviously we don't have different thermal expansion, so we've got to keep it the same. In a way I'd sort of like to do it in aluminium, but I know that's going to cause me all sorts of pain, so I'm not going to do that. So this is a 30mm piece of stock. Just do a rough mark for the length. And I'm just going to use the entire diameter basically. We'll just clean up the face or the surface here, make it look pretty. So this is a pretty large amount of material we've got to move out of the inside here. That's 17mm deep hole basically. And the internal dimensions have to be pretty accurate because we don't want it like waddling around on that shaft. So for now I'm just going to use a couple of different drills to knock it down, get it into a size that I can actually start using a boring bar with. And because of my mini lathe, I can't actually use a large drill because I don't have the distance to actually fit it in here. So I'm actually opening up to the biggest dimension. I think this is a 10mm end mill which I'm using here just to try and give me a bit more working space. And as you can see, there's not much working space with this boring bar, so I have to fiddle and dance around here to try and chop out this hole. You can actually see the material moving around here, and we're running it at high speed as it's sort of like shoving the material around a bit, but it'll come down once we get enough space to sort of work with the tool. Should be getting closer to the final cut here. Yeah, not quite. Alright, so this should be it. Let's see. Yeah, it goes in there nice. I think that's going to be a good fit. Knock a couple of chamfers in there. Now the actual length of this spacer is pretty critical, so instead of just doing a parting job, I'm actually going to try and use this tool to machine that internal face the best I can to the right dimension. I mean, I could part it off and try to machine it, but it's going to be a real pain because it's very difficult to measure the exact distance. But if I'm machining down like this, I can get the calipers in there and actually measure it. So I'll go as far as I can with this tool, without whacking into that chuck, that is, anyway. And for the final part, I'll just use a parting tool to chop it off. It's going to leave a bit of a messy edge, but we'll flip it over in a second here, and we'll face off any of the junk that's left on there. You can see I've got my finger on there applying pressure to stabilize the tool, and that actually helps quite a lot. Just really skim the face. I don't want to take anything really off here. And obviously we can chamfer it off while we've got it in the chuck here. Finishing touches. And there you go. Beautiful. So this is what the stack up looks like. Just try and get all the bits on here. And that's what it's going to look like when everything's put together. So to secure the shaft of the motor, I'll have to put a grub screw in this location here, and I'm actually putting it right through, so there'll be a grub screw on each side. It's actually a really snug fit. You have to really, it's not a friction fit with the way that the shaft fits in there, but even so, we're obviously going to have to lock it in with the grub screw. If I only lock it down with the grub screw on one side, then that's sort of going to create a deformative pressure that will still push a little bit off center. So the idea is to put a little bit of pressure on both sides and hopefully maintain the center while stop the shaft from spinning around. Obviously it's a very low torque motor anyway, so it's not going to really have much of a chance of spinning around. You can see it's super tight there. And obviously those grub screws are going to be a problem sticking out because the bearings have to go over the top of that grub screw. Yeah, so slight modification, and that's the way it sort of fits over there. You can see that the bearing's got to fit on top. So off the heat treating, you've seen this in a couple of the earlier videos, just got to get up to red hot. I'm actually going to try with a second torch in this video, see if we can improve the heating performance. Yeah, that's getting pretty red hot pretty quick. And it's even more critical here for the shaft, where I want to have the whole length of it heated. And you can see I'm using a drill to spin it to make sure that we're getting a constant heat on all sides. And this worked pretty well. You can see it got up to a good temperature here and got nice and red and hot. Ready for a Duncan. So my typical odds of getting a good finish, or a usable, or a finish I don't need to polish off, is pretty much the same as always, 50-50. So for the shaft here, you can see at the bottom here, a lot of it's just fallen off, so you're just going to have to scrape it all off, which is a pain. We're going to try and get the collet chuck mounted on here while I've got it centered in the lathe. I thought that would be a good way to do it, because I can, it's easy to spin it around to center it. A heap of green Loctite. So this collet chuck is really weird because the outer side is really quite tight. In fact, I had to file it down right to get it to fit at all, which is already a little bit of a concern. But the inside diameter of the hole is oversized. It's like conical, basically. It's really weird. And so basically there's not really an easy way to adjust it with just those two grub screws. So I'm basically just having to tap it around with a hammer and mess around, and yeah, basically I'm saying basically too many times, but it's going to be pretty tough to get this perfectly centered, and all the heavy lifting for maintaining that center is going to the Loctite. And back to looking at a diagram for a minute here. Compared to my original hand-drawn design for the outer casing, my new plan has me machining all the tricky geometry for locating everything into the actual internal structure of the case itself. Seems like a recipe for disaster if you ask me, but anyway, we're going to give it a go. The idea here for the change was to try to increase the overall strength of the case by retaining as much metal as possible. And I thought, worst case, if I messed it up, could always just cut it out and go back to the original plan. And another big difference between my original hand design drawing and what we're actually going to make is that I originally had the idea to use large headed bolts to retain the outermost bearing. But in my new plan, I'm actually going to make a separate retaining ring that will actually lock that bearing in place. Okay, with that said, let's take a look at making it. So this piece of aluminium round stock is actually a recycled piece of material. It was originally used to modify the stand of my wife's computer monitor, actually. It's like 20 years ago. It was basically too high to fit in the space we had, so I made this shorter little stand. And obviously monitors 20 years ago were really heavy, so I used a pretty substantial piece of material. Anyway, it's going to serve the job here for making the outer case of my spindle. Now obviously it's going to be a dual-sided operation where we're going to have to flip it around because I can't access all the material. We're basically going to use the entire length of the material as well. There's quite a lot of material we have to machine down. I think originally it was like a 70mm piece of material or something like that. And we've got to get it down to like 52. Maybe it's not 70, maybe it's 60mm. Anyway, there's quite a lot of material to remove. And as you can see, removing aluminium, especially when there's not much distance between the tool and the work material, yeah, it's quite a hassle because everything sort of just jams up and you get the aluminium trying to weld itself to itself everywhere. Not a lot of fun. Yeah, lots of this. Check that finish, doesn't it look beautiful? Oh yeah. 55. So we've got to get 52, right? God. $54. The progress is not great. You got to be really careful with this aluminium swarf or whatever you want to call it, cut off material. It's really very sharp and it'll cut you pretty bad if you're not careful, which is why I'm wearing the gloves. Bit more to go. Finally brave enough to use the auto feed, which sort of reduced the amount of work. And look at that. Took my glove off for a second and nice deep cut. 52.5, a little bit more to go. And the finishing is starting to look a little bit more reasonable. Wonder if there are any machinists out there screaming at their monitor. That's not the way you do it. You know, machinists are some of the most, vocal people out there, right? They all know the best way to do everything, right? But whatever, getting the job done. 52 on the dot, nice. Chamfer, just a slight chamfer. So this is actually the side where the motor will mount on. So I've got to open up the hole. And while at it, I'm just going to drill it all the way. Why not? Got to get through to the other side. Yep, that's through there. And just bore the internal dimension of where the motor interface is for the shaft. It's just has to be 13.5mm, right, for this side, I believe. Has to make clearance for the bearing. 12.5, sorry. 12.5. And there's also a little circlip or E-clip or whatever you want to call it on the motor retaining the shaft. And that sort of protrudes out, so we've got to make a little space here for that to fit in there as well. So that's going on there fine. You can see that little circlip or E-clip or whatever. So unfortunately, I've decided to use some SLA printing for this project because I can't use FDM because I've noticed this motor gets pretty hot when it's running. So I'm thinking that the resin material is going to be a little bit more, well, I know it's more resistant to heat. Unfortunately, it's a bloody mess to deal with. Look at this. It's impossible to get it off the surface here. But I'm getting a little bit better at the post-processing, considering I don't have any other weird machinery or anything like that to do it properly with. Anyway, I usually do a couple of cleans, 2 or 3 different cleans. Always switching to cleaner IPA every time. And look at this, look at that crack in that when I got it off. Thankfully that's only a jig, so it doesn't really matter for that piece of material. The other thing here is the outer ring for securing the bearing, which you'll see a little bit later when we use it. And there's a couple of other things that I'm printing as well, which I'm not showing here, but just showing the general process so you can get an idea. So this is the second cleaning. And after the second cleaning, I then get the alcohol and I'll just sort of run it over the top just to make sure that we get rid of any final sort of residue. And the big trick that I've learned is to use an air compressor to blow all of the remaining alcohol off. Don't let it dry naturally, blow it off, because that will stop any sort of resin being left over when you go to cure it. Otherwise you're going to get blemishes and nastiness on the surface. See, looks pretty good, right? Except for the bloody crack. So a couple of minutes in the curing machine will get it done. So this is what that jig is for. It's for the holes to mount the motor with. And I'm using the Dremel tool, which you saw me sort of make the mount for in the earlier episodes. And I decided to do it in the lathe because I thought it would be a good way to ensure some increased degree of accuracy of the location of the holes. Obviously the jigs are going to help with that, but this will also keep an equal distance from the center, so I thought that was a good way to do it. I'm not actually drilling these holes all the way through because when I'm boring or machining on the other side, I don't want the holes to come through. So I will actually do the final drill through at a later point in this process. See? There you go. Just some shallow holes. I've got the materials flipped around there, and this is where I made a really stupid mistake because that shim material I have is actually sticking out too far. When you're doing this sort of work, you really want to have as much distance between your checkpoints as you have. See, I'm moving it there, I'm only going a short distance. I really should have been checking right at the edge of the chuck there. But yeah, this is a bit of a mistake. So I'm losing a bit of accuracy here, which actually comes through a little bit in the finish as well. Thankfully, it's not that bad, but you know, it's something to remember when you're doing this stuff. So there's an existing hole that's coming through from the other side, but it's not going to be true to center. So I'm going to use this tool to cut the center. And then I'll just bring it down to the final diameter straight off the bat before we actually get into the most interesting part, which is going to be boring out all that material. Smart enough to leave my gloves on this time. And this is where I think I'm struggling a little bit trying to get this to match up perfectly. You can sort of see where I'm already cutting in on one side, but it's still got a little bit of a ledge there. It's not that bad, but it's a bit annoying. It could have been better. Nothing that a bit of Scotch-Brite won't fix. face it down to the final length. Just measure that, 65 mil. Yeah, good enough. Yeah, so this is the tricky part. There's a huge amount of material we've got to bore out of the inside of this case. And additionally to that, I also need to machine all of that very intricate geometry at the back, right in the back of that case. It's like 63 millimeters deep. So I'm not really sure how that's going to work out. But I'm not going to bore you with me hogging out all of this material because it's a pretty long and painful process. So I'll jump most of it in a second here. I'll just give you a taste of it, right? Enjoy the pain. Yeah, so here I've pretty much got it done. I think I'm using an improved technique here. I've actually cut out the center and then I'm just machining along with the waves a little bit more. Makes it a bit quicker. And of course you can't see what the hell's going on, which is going to make for some pretty boring footage once we get to machining the internal dimensions. So we're pretty much getting onto the final face now, and the bearing should, yeah, fit. Very nice. So we'll just stick 2 bearings in here, and this is something else that I've printed in the resin. But it's got a bit of an elephant's foot on it, so I'm just going to knock that down. And the face is not that true either, so this is a good opportunity just to true up that face. Now obviously the height is somewhat critical, but I have some ability to adjust the overall sort of fitment by adjusting different pieces. But as you can see here, that actually lines up really, really nicely. It's just meant to be on the inside just a touch, but yeah, that looks really good. Look at that. Oh, what's this? High-tech toys. This is a $3 endoscope view, which I got off AliExpress. Eat your heart out, A-Bomb79 or CE. They don't give you this sort of high-tech stuff. You can see a bit of the chatter in the back corner of the board there, which is what's to be expected with my sort of level of skill. But overall, the finish looks pretty good. So now we need to machine all that geometry in the back. Now, when I started using this endoscope, I thought it was just going to be something to give you a bit of a look at what's going on, but it actually turned out to be a great tool for doing this machining because you can't see what's going on, and honestly, I can't see what's going on. So here you can see I'm touching off and then checking the depth position. So that's already helping me. And yeah, now we're going to start machining out the space for the thrust bearing. So I won't talk too much, I'll just let you watch. Yep, if you can't see, I can't see. So here's the thrust bearing, and can you believe it, that fit is really good. Now I'm calculating the fit off the internal diameter, which is what the bearing is, and working from there to figure out the amount of cutting distance, and it actually worked out to be pretty spot on. I don't have a DRO or anything like that, I just have those little marking gauges that are on the wheel that you see me spinning. That's all I'm working with. And it's not actually all that accurate either, but yeah, that's why you see me fidgeting around a lot, sort of checking and rechecking and rechecking and cutting a little bit, messing around. So now I'm just cutting this to the correct depth, since I know that the size is pretty much right. Which is why I only cut a little bit first time, because I didn't want to cut all the way to the depth and then find it's too big, because then it's going to be unusable. And actually the front end of this material I will actually cut down in a few minutes anyway, to make space for the screw heads. So the overall height of the stack for the thrust bearing, I measured it with the calipers, and it was like 4.98 millimeters. So I want to have it really as close to that as possible to make sure that the bearings The main bearings are applying pressure onto those thrust bearings, and they're not just sort of like floating there. That would be quite useless if they were just floating there. All right, check the depth. Yeah, a bit more to go. And that's what we got. It's 498. It's pretty much on the money, right? But the bearing is really tight in there. In fact, too tight. I have to use this hook to try and get it out. So it's not actually going all the way to the back there. So I just need to just touch off on the surface of the diameter there, just to make sure that it will actually sit in there all the way. In fact, I'm cutting off so little you won't even be able to see it. Basically, it's just a little bit of material flew off there. So we'll try it again. Yeah, it's sitting there just right. It's not moving around, so that's good. But it's not too tight either, so that's really good. So now we have to make a space for the screw heads for where the screws will actually go. But we have to leave a ledge on the outer diameter for the main bearing to actually sit on. So that's what we're going to cut out, is another piece of material here. So I'm touching off again just to make sure I've got the distance correct. You can see I'm actually using the endoscope here again to help me with that. I can see I'm scratching or not scratching, and I know I've got the distance right. And the diameter of this is not super critical, but I want to leave enough material so that the bearing will have a decent amount of surface to push on, or the outer rim of the bearing, right? You can see that ledge there, but obviously this cut has to be deep enough to, and obviously big enough to actually allow me to have the heads of the screw to fit in. The depth also is not super critical, so I'm not overly worried about that. I think what I'm trying to say is it's not that critical, right? Just chop out a space somewhere to put the screw heads and we'll be okay. Since we're machining so close to the edge there, a lot of that material always piling up in front of the camera, which is a bit of a hassle, but thankfully, as this is not so precise, it's not that bad. I don't really care too much. Let's speed her up and we'll go for the finished cut. And finish the inside surface as well. Here we go. There it is. Just check that. So we've got 3 mil. Should be enough. Better get on the right way here. Here we go. These thrust bearings have a large hole and a small hole, basically, and this small hole should be on the thrust surface. Just do a fit up check just to make sure everything fits in here. And oh, may as well stack it up. There's the center spacer, outer spacer, and the outer main bearing. Oh, look at that. Looking really good. So here's another jig, and I'm going to use this jig to make all of the holes for mounting the retaining ring for that outermost bearing. I'm going to torture myself with this Dremel again, and this first bit is not drilling it at all. Bit of WD, and I think this bit has got to be blunt, right? Nah, it's not working. Alright, try again. Oh yeah, that's cutting a little bit better, but it's bloody hopeless, this Dremel, I tell you. You'd like to be able to reduce the RPM a bit because it's obviously running too fast, but at low RPM this Dremel just doesn't turn. It's just hopeless. So this is a good thing to do, is to put a pin in there to make sure your jig doesn't spin around while you're working on it. And yeah, I'm doing that because I made that mistake. Yeah, so I managed not to show you me opening all these holes because it just took so long to open up with this Dremel. So yeah, we'll just skip. So this is the last one I'll show you. Yeah, traumatic right to the end. But it is doing the job, so I guess that's a good thing at least. So I know if I did this in the drill stand, I'd definitely mess it up for sure. So we've tapped these holes, and I don't have a better way to do this other than doing it by hand. Probably should have a better way, but it is what it is. So as you can see, I'm doing a two-stage tap. So this is the second stage now. I'll just finish out the holes to the bottom. You can see I'm doing them pretty deep too, and I think that makes sense. There's no reason why not to. Just tidy up with the chamfer on all those holes. And this is the retaining ring. It's got to go on there like that. It's got a little ledge, so it sort of locks itself into place there, which it's doing. Just screw it on there. As you can see, it's a little bit oversized and the finish is nasty. And that's sort of by design, and also because I know this is the way that this is about the best quality that we can get out of that SLA printer. What I found is when you're printing, it actually will bleed the UV light, and it actually sort of grows a bead around the edge. So we'll just take that off with the lathe. Surprisingly, machining the resin material works out to be really good. It comes up with a really nice looking finish. Just like that, right? Looks really good. And I'll put a mark on here so that I can always put it back in the same place, because I'm sure the holes are not going to be 100% accurately located. Final touch, internal chamfer, and a bit of a tidy up. There you have it. Look at that. It's bloody awesome, actually. Nice. Got to draw those holes out now. So those holes that I originally opened are actually a little bit undersized, intentionally, because I knew I was going to drill them out anyway. So I've got one there and I've locked it in place so it doesn't spin around on me. Good practice. And the inside of the holes are all burred up from drilling through, so just clean those up. And chamfer the outside side of the holes while we're at it too. Look at that. Very nice. And the inside. Yeah, pretty good. I also need to make a hole so that we can actually access the grub screw that affixes the shaft of the motor to the shaft that I made. So I just located this hole as this, and I'll just put a chamfer on it to keep it tidy. So let's have a look at how this thing goes together. You can see that I've already sort of machined the heads of these screws and the length of the screws to the right dimensions first. I think most of this is self-explanatory, so I don't think it's too much I need to explain really. But there is an order of assembly that I have to sort of be careful about. I'm not sure this is the right thing to do or not, but I decided to stick a bunch of bearing grease on the thrust bearing. Seems bearings usually have grease on them, so why not, hey? Somebody's screaming at the screen again. No, don't put the grease on the thrust bearing. So just put this bearing here at the front here just to hold the shaft in the right orientation, while I use the hex wrench to lock down the grub screws onto the shaft here. Internal spacer, outer spacer, and outside bearing. Goes in there nice and tight. Look at that. Now, actually, haven't put any green Loctite on here as you see right now, but there is just a tiny little bit of play between the housing and the bearing and the shaft I made. It's basically nothing, but there is just a tiny little bit. So otherwise it's not going to fit together really. I'll be press fitting it. So to get rid of that on the outside bearing, on the shaft and on the body, I actually did use some green Loctite, which I'm not showing here, but I added that later, and that gets rid of any of the play that's in the shaft there. So yeah, spinning really smooth. Don't feel any resistance, and even though there's no green Loctite, very little play. So the first bench test I did with this motor showed it was getting pretty hot pretty quickly. You can see it's like 45-ish degrees just from doing a very short run. And all of the heat is right down at the bottom there on the stator component. So I thought I'd do some tests once I'd got it all put together to see how it managed with the heat. So this is a run where I think I'm going to run it for about 40 degrees or so, 42 degrees. Let's see how long it takes. Speeding it up here for you obviously to save you some time, but in the end it took around about 3 minutes to get to that 42 degree mark. And you can see the heat right there at the base of the motor, and the motor mount itself is also getting to a very similar temperature as well, right? So now we're in the cool down phase, and it really took forever to cool down, and you see that basically the heat is just like going evenly across all of the motor and the mount. Everything is pretty much turning the same color. And I think I waited like 45 minutes or so in this recording, and it still didn't get down to room temperature. It's like 25 degrees or something like that at 45 minutes. So that's just, you know, really not a good situation. So I had this PC fan, I'm sure from a very old CPU, as you can tell, and I put a connector on it there, and the idea is to mount it onto the body, because the body, you know, was having the same temperature as the motor, so hopefully this is a way to transmit the heat and get the heat away. So to mount it, I'm just going to put 2 screws into the heatsink itself, and to screw to that we obviously have to open up a couple of holes here, which I'll countersink. Just get rid of any of the sharp edges that will mar up my beautiful spindle that I made. Get this fan off for a minute, and we're just going to tap 2 M3 screw holes in here with what is clearly a very blunt drill bit. It looks to me like I'm tapping that at an angle. Maybe it's like some sort of optical effect or something, but anyway, it's going to do the job. So we use some thermal paste, because that surface, you can see it's like a really rough surface, so we want to have good thermal conductivity between the mount and the heatsink itself. And yeah, let's stick some blue Loctite on there just so that it doesn't get loose from vibrations or anything like that. I doubt it would, but anyway, just in case. There it is, looks good, right? That's what it looks like when it's mounted, and I'm using the cable for the laser and the 12-volt power supply of the laser to power the fan, because obviously I'm not using the laser, but I'm using the spindle. And let's run that test again, see if it's improved with the fan running. You can hear that spindle doesn't sound like it's quite balanced. I'm going to check the Runout in a minute. But anyway, for now, let's compare these 2 temperatures. You can see at the start here, they look pretty similar actually, though the fan and the heatsink is starting to take up the heat. So 3 minutes is what we got to at 42 degrees, and you can already see it's quite a big difference between the 2 temperatures, about 5 degrees, so that's doing something, I guess. And you see that the temperature of the body is actually a lot lower, so the heat's obviously sucking out using that heatsink. That's good. So 5 minutes and we're up to 42, 6 minutes 44. So yeah, it's doing something. Let's see what the cool down cycle looks like. And I've got these side by side again from the point that the motor was switched off. And you can already see that 26 minutes and we're already down to room temperature. So that's a huge improvement over the old one. So we'll look at the old spindle first, the old DC motor spindle, to see what the Runout looked like on that first, to get some sort of reference. So yeah, it looks like close to 0.1 millimeter total Runout. And the new spindle looks worse. What's going on with that? So I took the chuck off, and we'll just check the run out of the shaft first to see what it looks like. And that looks like around about 200ths. And there's not really any play around about half a hundredth of a mil, so that's looking pretty good. And after a bit of investigation, I'd actually discovered that the collet itself, I had actually two separate 3mm collets, and the collet itself, or one of the collets, was extremely out of whack. And there's a great video done by this old Tony about poopy collets, as he liked to call it. And it sort of stuck in my mind, and I went back and referred it, and then I remembered there are bad collets out there. And actually, it was true. One of the collets was bad, which is why those readings were so bad. But I hadn't realized it. So I took it off and I checked it, and I decided that when I was going to put this chuck back on, I was going to make it so that I could actually adjust it in an accurate way to get it fully centered again. And so as you can see, I've added grub screws in a total of 8 locations, and a bunch of green Loctite again to obviously secure it all in place once we get it positioned. And hammering it all the way home is a bit of a mistake. You shouldn't do that. But anyway. A lot of fiddling around, adjusting all of these. But now, obviously, we have effectively 2 4-jaw chucks at either end of the shaft attachment point. So there's plenty of adjustability here to get it dialed in. And the best place to adjust it, or to measure it, is actually the inside cone of the collet chuck. So what I'm doing here is only roughing, but in the end of the day, you really want to make sure that this inside cone position is perfectly centered, and the extreme end of the collet chuck is also centered. And if you get those both centered, then you're going to be looking pretty good. And then it just comes down to your problems with your collets and how accurate they are. So this is post adjustment, and I've just put this 3mm bit in here, and this is the reality of what it is. I've just stuck it in there. I haven't messed around with it. No tricks or smokes and mirrors or anything like that. It's 2/100ths of a millimeter, which is pretty good, I think. That's less than a thou, which is 2.54 hundredths of a millimeter, right? So I think that's looking good. So here I'm going to show you. I'm going to swap the bit, and we're going to do it again. So this chuck, this collet that I'm using is actually not too bad. It's not perfect, I'm sure, but it's pretty good. And after swapping out this bit to this 0.6, which is working, you can see again that, well, it's probably under 200. So I think it's a damn sight better than I used to have, even though it was probably a collet issue with that old spindle. Okay, let's take a look at how it all came together with everything wired and tidied up. We'll start with looking at the back first, since there's not much to it really. We have the power supply, which I've capped the ends with 3D printed covers and added the necessary connectors as well as an LED indicator. I even printed some nice little feet in TPU for it as well on the bottom here. To connect the power supply to the EC, I'm using this thick XT60 link cable which I made. I also set it up so that the EC can run from the little 12-volt power supply which I used for the laser. But given the lower RPM and lack of power, I really don't know how practical that's going to be. I also ended up 3D printing a simple case for the EC so that it was better protected from the elements, and it also makes it much easier to mount there right on the back of my original cable management box. The 3-phase motor wires then just go up and over to the Z-axis assembly. I switched around to looking at the front here. You can see the motor is mounted here in the lowest possible position where the wires just hit the mount, but it still has some adjustability, being able to move upwards to accommodate longer bits, and that should naturally going to increase the amount of working space you can deal with. And the way that I'm actually managing the cable from the motor to the fixed part of the Z-axis is that I made this little 3D printed clamping cable management part. The cables then just go around to the other side here where they're connected to the 3 ESC cables, so I can remove those easily enough. You can also see here where the Hall sensor connector is located here for now, and the position is such that it's going to be easy enough to use once I eventually get my censored ESC built. And to remove the motor, the cable clamp is easy enough to remove with a small hex wrench. And I know I'm going on a bit about the cable management and whatever, but it's actually pretty important in the case of this motor, since the case of the motor is spinning out in the open here. Originally, actually, I didn't like the idea of that much, and I was thinking to actually add a little cover over the motor, but in reality, it's actually better just to leave it out in the open where it can lose heat naturally. And actually, once I started using it, I found it really nice to be able to manually spin around the chuck from above like this. It works out to be pretty convenient. Now, unfortunately, I can't really show you a great demonstration of the spindle working in this video, but in a future video, I do plan to do a much better demonstration. But in any case, for now, here's a quick demonstration so you can at least see that it's working. And there you finally have it, all done. Can't tell you how happy I am to see the end of that one. Overall, the DIY brushless spindle seems like it's going to be a success, but I don't really have anything to compare it against, so I can't really say for sure. But either way, it's definitely going to do the job, and clearly a big improvement on that crappy DC motor spindle that I was using before. In the next episode, I am planning to see if I can test and demonstrate how well the rebuilt CNC and new spindle perform. I will also likely touch on the good and the bad and possibly some regrets with regards to this overall project. And as you saw in my last community post, I've already actually started to do some PCB testing, so hopefully soon enough I'll be putting out a couple of PCB related videos and likely a couple of Arduino tutorial videos again soon too. Anyway, it takes a heap of work to do these projects and just about as much, maybe even more work to actually produce these videos. So I'm probably going to take a bit of a break here and there. So expect the video release schedule to go back to a much more manageable one video every month or so. That should hopefully help to maintain my sanity. Now, I can't say that I'm completely immune to feeling a bit bummed every time I release a video consisting of weeks or months of work, only to actually be seen by a handful of people. So lowering the frequency gives me a little bit more time to recover, and in turn gives me more time being in a generally happier mental state. And for those of you who have managed to watch right to the end, I do hope you enjoyed, and I hope it wasn't too much of a struggle to watch. And of course, I do hope to catch you in the next one. So, I'll see you then.